Hi. Excuse me. So for the assignment 4, for the enhancements, it says some data definitions. Do you recommend us adding our assignments?
Can we talk after?
Yeah, sure.
Okay. Sorry, that's live.
Oh, sorry.
There we go. All right. So why doesn't everyone start out by taking a few minutes and looking at this recursive function we have here on the slide? So we want to produce a function that's going to look at two lists, element by element, and it's going to count the number of elements that are equal between the two lists. And when we're saying equal, we're not saying, okay, list 1 also contains the number 1. We're saying, no, element 2 of list 1 is equal to element 2 of list 2. So it's in place equals. So take a few minutes and see if you can do this. Note that there's no requirement on this function that the two lists actually have the same length. So see if you can do it, and then we can look at a possible solution. All right. So I know there's not a lot of time to think about this particular problem, but to start out with, let's think about how do we actually do recursion when we have two lists that we actually want to recurse on. We have to take into consideration there are 4 possible cases. Those 4 cases, of course, are both lists are empty. The first list is empty, but not the second. The second list is empty, but not the first, and both lists are non-empty. And when we look at this problem, we know that if both lists are empty, they're equal, Because since they have no elements, we should produce 0. Empty is not an element. Empty means a list. It's just empty. There's nothing in it. Then we have to take a look at the cases where one of the lists is not empty, but the other one is. Well, if that's the case, then the two lists don't have equal length, and there's no sense continuing recursion because one of those lists is now done. And so those should also be base cases. And they should also produce 0 in both of those. So to go over and look at the solution, I haven't talked about the recursive part yet. Give me a second here. There it is. So I've taken the base cases, and instead of having all 4 of these different cases like the template would allot, I have actually taken the 3 base cases and put them all into a single one. Because if both lists are empty, we should produce 0. And if one of the lists is empty, we should also produce 0. So I said if list 1 is empty or list 2 is empty, produce 0. So all 3 base cases combined into one nice thing. Then I look at my recursive cases. There are 2. If the first element of the first list is equal to the first element of the second list, then we have equal elements, and we should be adding 1 to the results of counting how many elements are equal in the remainder of the 2 lists. Otherwise, we add 0, or simply return the result of computing the number of elements are equal in the remainder of both lists. So there we have both cases. Any questions about how this works? All right. Yep.
To make a test case for this, would you make a test where one of the lists is empty and one is not?
Yeah, so making test cases for this particular function, one of the things that you might remember from earlier in the term is when you're dealing with an and or an or expression, you actually have to make sure that there's a test for every combination. So in that case, you would need to have all 4 of the proper tests. So you'd need to have 1 for 2 non-empty, you'd have to have 2 empty lists, and you'd have to have 1 for the first list is empty and 1 for the second list empty. You have to test every possibility. Yeah?
Can you add the second element of the first list equals to the third element of the second
Yeah,
list?
so what you're saying is the second element of the first list is equal to the third element of the second list. We don't care. We're looking at an element-wise, like a lockstep comparison. I want to know, is the value at index 4 in my list, or position 4, equal to the value at position 4 in the other list? So if it's some other position, we don't care. Yeah. All right, any other questions about this particular function? Okay. If you have a clicker, now would be a good time to get it out. And I know you're probably sitting there, oh, the clicker's working today, that sucks. Well, it's working today. I'll give you 2 a minute, by the way. All right. So, always a few people in the last second. Let's see what everybody says. Lockstep requires both lists to be processed at the same rate. That's correct. Because literally what we're saying is we're always processing things at exactly the same rate. So it's not any of the others. Now you might be asking yourself, am I ever going to use this concept of lockstep outside of this course? Yes, you will. Especially if you continue on in computer science. You'll do it with arrays and other data structures. And if you go into any kind of data sciences program or machine learning or computer graphics, you might get an opportunity to work with GPU programming. That's your graphics card. And your graphics card, which you may not know about it, is that instead of having, 4 or 8 cores, cutesy numbers of cores that your Intel or AMD chips might have, your graphics card has thousands. But there's a restriction. They have to be executing the same instruction at the same time. They execute code in lockstep. So this is actually a very common thing. It's not just something we made up for this course. All right, we've got 2 more clicker questions. Again, I'll give you a minute to do it. I've already given you the answer to this one. All right, so let's see what everybody says. Most of you say C. So that is correct because there are 4 cases. Both lists are empty. The first list is empty but not the second. The second list is empty but not the first. And both lists are non-empty. And regardless of whether your function that you're implementing can combine some of these cases together, you should still consider, when you're doing your planning, all 4 of these cases. And then if you can combine them later, that's great. All right. One more. Always got to ask questions about contracts because when it comes to the exams, you get tested on that. All right. So let's see where everyone fell on this one. Most of you said D. D is correct. All right. So you have a function that consumes a natural number, and it's going to produce something of one of three possibilities, either a Boolean, a string, or the number 10. Now, you could, technically speaking, say B. It's a function that consumes a nat and produces anything. Well, yes and no, because the problem with that particular contract is it isn't specific enough. If I'm presented with that contract, then the only way that I can appropriately respond to that is by saying, okay, I need to be able to handle symbols, lists, functions. I need to be handling any kind of output possible. And that's simply not true, because this function only produces one of three different kinds of things. Now, you could say C, but that's not, number one, it's not precise enough, because I can't produce any natural number, I only produce 10. And furthermore, that's not the syntax that we use in a contract when there's multiple options. So if you remember, it's a few slides back in Module 8, that when there are multiple possibilities for what a function can consume or produce, you use this any of notation. So this can do any of, bool, string, or 10. Yep?
Because it should be none.
Pardon?
For the D, it should be none instead.
No, it shouldn't be nat, because we don't produce any other natural numbers other than 10. So I could say nat, but then I would have to consider the fact, oh, it could be 0, 1, it could be any natural number. We're not producing any natural number, we're only producing 10. So you should, if there's ever situations like that, where you're only saying, let's say a function only produces false. I don't know why you'd write a function that only produces false. But let's say you did. Then the contract, it wouldn't be specific enough to say it produces a bool, because it only ever produces false. So say it produces false. Always be as precise as possible. The thing you have to keep in mind about contracts is this is really the only thing that you have to communicate with your user as to what the behavior of this function is. So you've got to be as precise as possible. All right, any other questions? Yeah?
So if you just use your function like, let's make negative numbers or something as an output, but it has decimals, would you say positive num, or would you say num?
No, what I would say is, so I would say num, and then I would add a requirement section, and in the requirements, I would say it has to be greater than or equal to 0.
So how is that different from this?
Well, in this case, we don't have a requirement section. So we could have put a requirement after this to say the nat is equal to 10.
So how is that required if you're not requiring anything of like, if the function already does that, then why do you want to require?
It's the goal of the contract and the requirements is to convey as much information as possible to the user about how the kinds of inputs that are expected and the kinds of values that are being produced. So if we say nat, that would lead our user to believe that any natural number could be produced. But the truth is, only 10 is the natural number that could be produced. So if I say nat is being produced, then the only thing that would really be acceptable to clarify that is to either change it to 10 or to have a note below saying the natural number is equal to 10. So in the case of, let's say we were consuming a number that could be decimal but not negative, I would say num in that case, and then I would have a requirement below that indicates the number has to be greater than or equal to 0. So you should always aim to be as precise as possible. All right, any other question? All right, couple things before we get back into the notes then. Of course, assignment 4 is due today, yes? Yeah, okay. And assignment 5, you can get started on that. And hey, next week's reading week. It's nice for everybody, right? I can tell you when I was an undergrad, there was no such thing as reading week. We didn't have one. It didn't exist. At the end of my undergrad, we got reading day, and only in the fall. Yeah, it wasn't fun. Engineering gets a reading day? Yeah, but they're engineers. We don't care. We're mathies. Or not engineers. All right, so on that note, if you've been on Piazza, I have posted a packet of sample problems that cover up to recursion, roughly up to recursion, so not including recursion, and I will try to post some more sample problems in, hopefully by the weekend, that will cover some recursion. And I'm also working on a sample midterm so that you have lots of materials for you to study CS135 over reading week. Although I'm going to make the assumption that even though that's, the purpose of reading week, study for those exams, that most of you are probably going on a vacation. Whether that is a vacation somewhere else or a vacation into a video game, I don't know. How many of you are actually going away? Couple people, not too many. I'd avoid cruise ships right now. All right. So yeah, all of those sample stuff will be posted to Piazza. There's already some problems there. Make sure you look at them. All right. Then where we left off last class was looking at recursion on two lists, and specifically we ended looking at recursion on two lists where we process each list at a different rate. And the best example of a function for this is actually merging two sorted lists. Now, there's different ways that you can create a template for this, and actually what we discovered last class was that you can't actually nail down any one template. And the reason for that is even though we can nail down the form of the questions for the template, the fact that there are 4 different cases, the 2 lists empty, one of the lists empty, and the other one not, and then both lists non-empty, what we do under most of those cases really depends on what kind of problem you're solving. So for example, we do know that if both lists are empty, you're probably not recursing on anything because everything is empty. That's probably a base case. But when one list is empty and not the other one, it may be a base case and it may not be a base case. It may be a recursive case. So it kind of makes that part of the template a little tricky to write. And then when it comes to the case where both lists are non-empty, we just don't know what to do because we may recurse on one list, we may recurse on the other list, or we may recurse on both lists. And what we do really depends on what kind of problem you have. So it makes this template very difficult to write. That being said, they took in the notes the template that they've given and they filled it in to give you merging 2 sorted lists. So if you take 2 sorted lists, we're going to merge them, produce a single sorted list. And yes, it follows the template, but this is very ugly. You've got nested conditions. You've got a bunch of cases which could be combined together. You keep getting these cons predicates. They really like that cons predicate. I really don't like that because it's usually unnecessary. So this is a long-winded solution. It is technically correct. There's a better way to do it. And I have that in a racket here. Let's go over. And here's the other way that you can do it. So I can do this by noting the fact that if the first list is empty, I can just produce the second list. And that actually takes care of 2 cases in one. Because if the second list is empty and the first list is empty, then if I produce the second list, I'm producing empty. And if the second list isn't empty, I produce the second list, which was the desired behavior of the second case anyways. So we can combine those 2 cases into one. And then we get the other case where the second list is empty but not the first. And then no nested cons here, no cons question mark predicate. If both lists are not empty, then I compare the 2 first elements. If the first of the first list is less than the first of the second list, then I cons the first of the first list onto the result and get merging the rest of one list with the other. Otherwise, I'm going to take the first element of the second list and merge that in the remainder. So the recursive cases are the same, it's just a little tidier. Now, You may find this implementation here intimidating, because you may look at it and be like, I don't see where you got that from. That's 20 plus years of experience coding with Scheme. I don't anticipate that you're going to sit down at any point and just pop this out like that. Unless maybe you're a Haskell programmer or something for the last, since you were 5. In which case, I'm sorry your parents introduced you to Haskell. Now that being said, even though this is a great solution, and it's much simpler and much fewer steps than the one that's provided in the slides, when you're first solving this problem, this is what you should aim for. Don't worry if you don't come up with solutions that look like ours off the top of your head. This isn't a course about challenging you to create the most beautiful code ever written. We don't expect that of you at all. Always do your planning and then write your code, and don't worry if it's a mess. Don't worry if it looks like this. That still works. But if you have some time, go back and refine the code. Look at it and say, can I get rid of this nested con? That would be the first thing that I would do here. Can I get rid of the nested con? And then after I get rid of the nested con, I would ask myself, can I get rid of these ands? Because that's a lot of extra work. So start with the solution you can get working. No matter what it looks like, get something down. And then if you have time, come back. See if you can make it better. See if you can make it cleaner, tidier. Don't worry about producing the most beautiful solution off the top of your head. That takes years of experience to do that. Most of the time. Except those, like super geniuses who are like CCC winners, I expect them to ace this, right? All right. So we can trace through merge here, and it doesn't matter if you use their implementation or my implementation. The condensed trace looks the same. We have the lists 3, 4, and list 2, 5, 6. And in our first application, we're going to take 2 from the second list, and we cons that onto the result of merging 3, 4 with 5, 6. And then I take 3 from the first list. And then in the third application, I take 4 from the first list. And now in my final application of merge, list 1 is empty. And so that's just going to produce the remaining list, which is list 2. And now we get merge of the sorted list. Now, what's really cool about merge is this is actually one of the major components of a sorting algorithm known as merge sort. And merge sort is a very, very great sorting algorithm. It's pretty much as good as you can do for comparison-based sorting. And you don't need to worry about why or the proof or anything like that. If you go take CS135, you will proof the crap out of that. We're not going to do it here. All right. So there are lots and lots and lots and lots and lots and lots and lots of different functions we can do. But let's say you wanted to write a function to test the equality between 2 lists. That's a very useful thing. You want to know, for example, is this list equal to this other list? Because if they are, then you're going to do some magical thing. So in order to test for list equality, we have to consider the 4 possible cases. That is, the 2 lists are empty, one of the lists is empty but the other one isn't, and then both lists are non-empty. So that's our template from before. It covers the 4 cases, and we could fill it in. And if we could fill it in here, we would say, well, if both lists are empty, then we produce true, because empty is equal to empty. And if one of the lists is empty and the other one isn't, we produce false, because they're not equal length, and therefore they could not be equal lists. And then in the last case, where both lists are non-empty, we would compare the first elements, and if the first elements of both lists are the same, we would and that with comparing for equality for the rest of both lists. Seems fairly straightforward. Now, they don't give you in these notes the ugly solution. Well, I guess they do. Here's the ugly solution. But they could give you something a lot nicer, couldn't they? So, this is what I just talked about. How could we simplify this? Well, one thing we know is that if both lists are empty, then we produce true. If one of the lists is empty, then we produce false. And then otherwise we do this comparison. We could simplify this here. So let's actually do that. So we could do something like, let's scroll down. Oh, I already have the solution. Woohoo! There we go. So there it is there. So if the first list is empty, I produce, is the second list empty? Ah, that's pretty clever, isn't it? I just combined a whole bunch of cases into one. Oh, it's interesting. So if both lists are empty, then that produces true. But if only one of the lists is empty, it produces false. So that just took two cases and turned it into one. That's fun. And then if list 2 is empty, I produce false. And then you can see that I have well, I've done some really interesting things here, haven't I? I got rid of the and altogether. Oh. Because I have an extra base case that they didn't. Do you know what the extra base case is? The first time we find two elements that are not equal to each other, stop. Why would you bother recursing if the two elements at the front of the list are not equal? If they're not equal, then there's no way the two lists are equal. So stop the recursion. Why not? Isn't that nice and simple? Yeah?
For the first case, you will use and, right?
No? No? No and.
I'm just asking for the second case, simply add like or some from this.
Nope. So the question is, shouldn't I have an or for the second one? No, because remember we evaluate the questions in order. So the first question is list 1 empty? So if list 1 is empty, regardless of what list 2 is, we'll go through that first one. Therefore, you know we would never even get to asking question 2 unless we know list 1 is not empty. So if you actually order the questions very carefully, you can get rid of all the ands and ors almost all the time. I don't expect you to be able to produce this off the top of your head. This is much, much more thought going on than what the solution in the notes has. But if you were to actually step through this and trace it, you would see it's significantly fewer steps of evaluation than the other one. So in a lot of ways, this is both faster and simpler. But the thought process as to how I arrived at this is a little more complicated, which is why I keep reiterating the fact, don't try to get this first. Go for the one that matches the template, and then if you have time, see if you can do this. All right, any questions about this list equal? So for the record, there's absolutely no reason for you to implement this because the function already exists. It's called equal question mark. Equal question mark consumes any and produces a bool, which means equal question mark can compare two lists for equality. And it does it just fine. It's not very fast. And we're not going to get into why it's not very fast now, but it is not a very fast way of doing it. All right. Now let's look at some other recursion. So we've done recursion on one list, and we've done recursion on two lists. What if I want to do recursion on a list and a number? So the example we have for this is, what if I want to know if an item appears at least n times? So maybe I want to ask the question, is there at least 10 people in CS135 that have played Breath of the Wild? And let's say that's the Zelda game that came out a few years ago, right? All right. So I've got a list of all your answers, and I need to find if there's at least N people here that have played that game. How are we going to solve that problem? Because I could count, I could iterate through the list or recurse through the list once, and I could count how many times Breath of the Wild happens, and then I could compare it to N. That technically works, by the way. But in order to do that, you actually should have a helper function, because you have one function that does the body of the work that's actually going to count the number of times Breath of the Wild appears. And then in your wrapper function, it would simply compare the result of that to N, and that technically works. And it follows everything that you've ever done with simple recursion, no problem. Could we recurse on both at the same time? Well, here's the interesting thing. We're asking, is there at least N copies of this thing in the list? I don't need to count if there's more than N. I should be able to stop counting when N has been reached. Because saying at least N, well, if I just count to N, then technically speaking, there are at least N copies. So we can combine the recursive template from numbers and from a list and get one joint template that lets us recurse on both things at the same time. So before I show you the template, of course, you're supposed to create the design recipe first. So there's our purpose, there's our contract. Note that we're saying a list of any. We'll use the equal predicates to make sure that we can compare two things of any type. And then we'll produce a bool. So here's a bunch of examples. And now we have our template. Well, our template has to combine both the template for simple recursion on a natural number and simple recursion on a list. So for a natural number, our base case is when N is 0. And for our list, the base case is an empty list. So now we have 4 cases again. We have N is 0, and the list is empty. We have N is 0, and the list is not empty. We have N is greater than 0, and the list is empty. And then we have the fourth case, which is N is not 0, and the list is not empty. And we need to take into consideration all of those possibilities. Well, let's think about the base case. If N is 0, that means I need to find 0 copies of the item. And if my list is empty, and N is 0, then I must have found them. So, produce true. If N is 0, and the list is not empty, then I have found all the copies that I needed to find because I'm not asking for any, so I produce true there. No point in continuing to search if you don't need to find any copies. If N is not 0 and the list is empty, then you produce false because there's no more items in the list to search through. So now we just come down to the final case where N is not 0 and the list is not empty. And now we need to think about what is N. Well, what we're going to do here is every time we encounter the item we're searching for, we'll decrement N. So the first time I find someone who's played Breath of the Wild, the next recursive call, N is now N minus 1. So if you start at 10, the next time it's 9. And it stays 9 until I find another person. And then it becomes 8. So we're going to use N to represent the number of people remaining to find. Hence, when it reaches 0, we found everything we needed. So what I'm going to do is I'm going to have to split the recursive case into 2 parts. The first part is if the first item of the list is equal to the thing I'm searching for, then I need to recurse both on N and the rest of the list. So I would subtract 1 from N, and I would use the rest of the list. If, however, the first item of the list is not equal to the thing I'm searching for, I don't decrement N, but I I still recurse on the rest of the list. Now, they haven't given you the complicated solution. They've given you the nice simple one here. And you can see it's quite clean. So if n is 0, we produce true. We don't care what the value of the list is. Because if the list is empty, or whether the list has items in it still, if n is 0, we found everything we needed. Stop. You're done. You found at least n items. If the list is empty, then we produce false. Now, again, this comes down to these questions being asked in a specific order. We only have to check if n is 0 first to produce true. And then if we move on to any of the other questions, we know that n is not 0. Which means we have more things to find. So if the list is empty, since we know n is not 0 because we've handled the 0 case already, we know that the item isn't in the list, so we can use that. Otherwise, there's us comparing for equality, and then recursing on both n and the rest of the list. And if they're not equal, then we just recurse on the rest. It's pretty cool, right? Any questions about that? There's a trace for it on slide 68, but I'm not going to go through this here. What I would like to talk about, though, is what kind of recursion is this? Now, I've kind of alluded to the fact before that this is probably not simple, but it's not simple by the definition we gave you before. But it's still technically a simple recursion. We gave you the definition before that said that you make exactly one step towards the base case and all other arguments remain unchanged. So that makes it interesting. When we have lists, when we have a function that consumes two lists, and one list is along for the ride, then that's very obviously simple recursion. If we're looking at lists recursing in lockstep, stop thinking of it as recursing on two lists. Both lists are moving one step towards the same base case. Oh, wait, that's just simple recursion. And then we think about processing the lists at different rates. Well, there are multiple base cases often. And each time we take the rest of the list, we are moving one step closer to some base case. So it is, if we expand our minds a little bit, still simple recursion. All right. So on that note, we are going to move on to Module 9 now, which is, guess what? More recursion. I know some of you are still probably holding out. When are we going to get to loops? We're not. So stop sitting there dreaming. All right. So as it turns out, even though all of this stuff is recursion, there are many different labels for recursion. We've seen simple recursion, but there are others. There's also accumulative recursion. There's generative recursion. There's structural recursion. There's all different kinds of labels that we can assign to it. Now, sometimes the labels are kind of a gray area, but not always. So what we'd like to do is to introduce you to some of these other kinds of recursion. And you might be thinking to yourself, well, simple recursion seems to solve every problem that I could ever want to do, so why would I bother with any other kind of recursion? We're going to show you why. So, just to recall the definition of simple recursion, you have every argument in the recursive function is either unchanged or one step closer to not the base case, a base case. Hence why we could technically consider all of the previous ones to be still simple. All right. So let's do another simple recursive problem. And this is another famous one. Let's compute the max of a list. So I give you a list of numbers, and I want you to write a simple recursive function to give me the biggest element from that list. And here's one of the possible solutions. So here's what we're going to do. If the list is empty, oh wait, it. You're not, you know what, let's just work on non-empty lists. That'll be nice. Because an empty list doesn't have a maximum, and we don't really have a way to represent that. So let's assume we're going to work on a non-empty list. If the list contains only one element, that is the rest of the list is empty, then the max of the list is that one element. Otherwise, I need to know if the first item of my list is bigger than the max of the rest of the list. So I'm going to compare the first of the list to getting the maximum from the rest of the list. And if that is true, then the biggest element of the list is the first item. Right. If it's not true, however, then I need to compute the max from the rest of the list. Now this probably looks perfectly fine. A little bit odd in that one of our questions actually involves the recursive call. It still works. But here's the problem. Let's suppose we have a list in increasing order. That is, our list goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the first of the list is 1. And so I'm going to compare 1, and then I have to get the max of the remainder of the list, which is 10. So since 1 is not bigger than the max of the remaining list, this question evaluates false. And so I go down into the else case, and I recompute the max of the rest of the list. So I just computed the max of the rest of the list twice. Now, some of you who've done programming before would be like, why don't you just put that in a local variable and reuse the result multiple times? Yeah, we're not doing that yet. So that means that for our list in increasing order, for each application of this function, we make 2 recursive calls. That probably doesn't seem like a big deal to you. But what if I had a list of 25 elements? Let's actually count how many recursive calls are going to happen. So we start with a list of 25 elements. Now, the list of elements are in increasing order, so we know each call to the max of the list is going to result in 2 recursive calls on the rest of the list. So my original call on a 25 element list results in 2 calls on a 24 element list. And since our list is in increasing order, each one of those calls results in 2 calls to a list of 23 elements. And each call of each one of those results in a call of 22 elements, and so on, and so on, and so on. And what we end up with, if you were to count up how many total elements there are here, it would be 2 to the power of 25 minus 1. That's how many recursive calls this is making. Now, maybe that doesn't seem problematic to you. 2 to the power of 25, it's not that big. I don't actually know what that is off the top of my head, but let's find out. This is not what Racket's for, right? Computing powers. Let's go over here. We're going to need some space. Of course it doesn't do that. There we go. We're nice and clear. So, what's that? We've got 33 million recursive calls to compute the max of a list of 25 elements. What? Yeah, that's a little ridiculous, isn't it? But you know what? It's a computer. It's a modern machine. You know, this machine's only about a year and a half old. That's not that bad. But what if my list had 100 elements in it? One of the nice things about Racket is because the numbers are unbound, we can actually do this. So, if there were 100 items in the list, that is how many recursive calls there would be. There's more than 100 of you in this class. There's more than 100 people at this school. If I want to do find this best student in the whole school right now. Let's assume that there are 28,000 people, which I actually think is a lot less than there really is. Well, let's assume there are 28,000 students at this school. Now I want to find the best one, the highest grades. How many recursive calls would that be? So how long does that take? It takes the age of the universe. We have a little problem here. Well, can we do better using just simple recursion? We can actually, as it turns out. I'm going to skip a few slides. Don't worry, we're going to come back to them. So how do we do a bit better? Well, we know that the problem from the previous implementation was the fact that we ended up in a worst case scenario where our list was in increasing order, calling the function recursively on the rest of the list twice, which leads to an exponential blow up of recursive calls, and that's horrible. Well, if we make a tiny helper function, we can actually get rid of the second recursive call. So we have this helper function that just takes two numbers and it's going to produce the bigger of the two numbers. Okay, great, fine. We can do that. Probably could have just used the built-in max, but why not? All right, so if I do that, if the list is empty, or sorry, if the rest of the list is empty, then the max is the first element, because there's only one element in the list. Otherwise, the maximum of the list is the max between the first of the list and the max of the rest of the list. So what we end up getting, square talk. I have no idea why there is like a square talk. Weird. What you would end up getting is something like that. And then at the end, we'd evaluate this all up. You'd get 4, and then you'd get 4, and then it would produce 4. So we eliminated that second recursive call. Now, how do we know? I mean, we know in our hearts that this is obviously more efficient than the other one. And we know that because if we count how many recursive calls actually happen, the number of recursive calls here in our worst case scenario list that's in increasing order is significantly less than the number of recursive calls in the previous solution. And what's interesting is this brings us to the topic of efficiency. How do you know or prove that one algorithm is more efficient than another? Or how do you even bridge the topic of discussing what it means for an algorithm to be of a particular efficiency? And what it comes down to is counting things like how many recursive calls there are. And as you move into CS240, if you choose to go that route, you'll be counting how many adds there are. You'll be counting you count everything. They're not free, by the way. So if we count the number of recursive calls for our original implementation of max list, it was 2 to the power of n minus 1. And if we count the number of recursive calls for the better solution, it's just n. Now we could do a comparison directly between the two, but wait, what's n? When we're computing the number of recursive calls, we want to do it with respect to the length of the input. N is the length of the input. So if we have a list of n items, then there are 2 to the power of n minus 1 recursive calls in the worst case for the first solution and n for the second. Now we could be very specific and say 2 to the n minus 1, but as n approaches infinity, does the minus 1 matter? Obviously not. I don't care about the age of the universe minus 1 because we'll all be dead. So nobody cares. So what we actually do is instead of using the precise count, we use this thing, which I'm sure many of you have seen in calculus, known as big O notation or order notation. And what we see is that 2 to the n minus 1 is actually big O of 2 to the n. Now, is there anyone in here who has never seen this before? Quite a few people. Okay. Let me show you a little bit. Now, I'm about to give you a definition of something that you don't need to know until CS240. So I will not test you on this. It's just to kind of show you where this all comes from. So what you've got is we're going to say that, I might as well turn a light on here. That'd be good. F of n is in big O of g of n if there exists constants c and n naught such that f of n is less than or equal to c g of n for all n greater than or equal to n naught. Now that's a lot of fancy math. And again, this particular definition you do not need to know until CS240, where you will prove everything using it. But effectively what this is saying is that if this is f of n and this is g of n, this, and well, let's say cg of n, then this is n naught. And what we're saying is that after this point here, g of n is the bound. It's an upper bound on the behavior. We know that f of n will never be bigger than that. That's effectively what we're saying, which means that a lot of things are in each other's families. So we could say, so 2 to the n minus 1 is in big O of 2 to the n. And I can also say 3n plus 5 is in big O of n. So they create these whole families. And when we're looking at an algorithm and computing its efficiency, we are often looking at what is the big O for that function. And so then what we're going to do is we get function A and function B. We compute the big O for one and compute the big O for the other, and then we compare that and we say, okay, well, which one is better? Now, in computer science, we don't usually see a lot of too many funky ones, at least in most algorithms. But these are the main ones that you may encounter in increasing order. So the best functions are big O of 1. We call it constant time. And they're called constant time because it has nothing to do with the size of the input. It's a fixed number of operations. Doesn't matter how big the input is, same number of operations every time. Constant time is as good as it gets. Log n is a bit better, or is not as good as constant time, but it's not bad, because if you have n is equal to 32, and by the way, our logs are all base 2, then this is 5. Not bad. And then we have linear, which is n, and then there's n log n. Now n log n is one you may have seen before if you've done anything with sorting, because comparison-based sorting, like merge sort and quick sort, that's actually as fast as they can go. They can't go faster than that. Again, the proof of that is CS240. And then things like insertion sort, they're n squared. And then our max list is 2 to the n, which is really bad. Really, really bad. Although I've seen worse. So when we're talking about, when you're sitting down and maybe you're on co-op term, or maybe you're sitting there thinking, well, I'm not sure my algorithm is efficient. Count how many recursive calls there are based on the input of size n. Count them for your both solutions. and choose the solution that gives you the smaller number. And by the way, if this stuff really interests you, big O has a bunch of siblings. There's also little o, there's theta, there's big omega, and there's little omega. Again, that's all CS240. CS240 is the course where you enter and you're like, yeah, I'm going to learn about data structures and algorithms, and it's all proofs on paper. So if you like proofs, great course. It's a fun course. I'm not trying to scare you. Yeah. I don't remember 135. You're talking about a course I took 20 years ago. Yeah, it's proofs. By the way, there's a lot of courses like that in CS. All right. So that's a little bit about efficiency. Now, one more thing I want to talk about. You may have noticed I keep using the terms worst case. Because when we're comparing two algorithms, does it really make sense to compare their performance on the best case? The best case is the first element of the two lists are not equal in my equal function, so I stop. That tells me nothing about the behavior of the function. The behavior of the function, you should always assume that the user is going to give you the worst case possible input. So oftentimes when we're computing efficiency, we're looking at what is the behavior of this function provided the input is the absolute worst possible input you could give it. And it actually can be quite challenging to figure out what is the worst possible input. We don't, by the way, always look at worst case. And a lot of times we'll also look at average case, because maybe the worst case is very rare, and maybe on average it does a lot better. So there's all kinds of fun math proofs and analysis there. All right. So that's it for simple recursion. Now I want, I still don't like our max list. I just don't like it. It's kind of ugly. Can we solve computing the max of a list in any other way? The answer is obviously yes. And in order to do it, though, we need to use a different kind of recursion. And the kind of recursion we want to use is called accumulative recursion. And what it's based off of is this idea of, instead of combining the nth item with the results for n minus 1, we're going to then take the result we've got so far with us. So, and if you think about it, this is how humans would do a max. If I give you a list of all your classmates, you're going to take and say, find me the person with the biggest grade. You're going to take the first person on the list, and you're going to say, okay, that's my maximum so far. And then you look at the second person, and you say, is it better than my max so far? If it is, the second person becomes your new maximum. So you're taking the maximum you've seen so far with you as you process the list. And that's what we're doing with accumulative recursion. We're taking the maximum of things we've seen so far and taking it with us. So we can solve max of the list doing accumulative recursion. And in order to do it, we actually need a wrapper function, because we have to, in order to do this recursion, we have to have a so far value. What have we seen so far? We don't want to expose that to our users, so we write a wrapper function. And this, again, is assuming a non-empty list is past max. And so I'm going to say that my initial maximum is the first of the list. And so I want to determine if this is the max in the rest of the list. Now, what do I do? Well, what I'm going to do is, if the list is empty, then whatever my so far maximum is, since there's no more items to compare against, then whatever's in the max so far is the maximum of the list. There's no items. Otherwise, if the list is not empty, I'm going to check, is the first item in the list bigger than the max so far? If it is, then when I recurse, I'm looking for the max in the rest of the list, and my so far value has changed to be the original first. If, however, that's not the case, then my max so far didn't change, and I just recurse on the rest of the list. It's not too bad, actually. This is actually quite tidy and quite simple. A little bit more natural in thinking, but sometimes people have a hard time thinking about it. So I want to give you another example of accumulative recursion. And what I'm going to do is I'm going to do it with a simpler problem. And then we'll draw out a condensed trace on the board so you can see the difference in the behavior side by side for both. So first, the problem we're going to solve is how do I sum the items in a list? So we'll do the simple recursion first. There we go. There's summing the elements of the list. Now let's do it with accumulative recursion. Well, when you're thinking about accumulative recursion, one of the things you need to think of is what is the result so far that I want to take with me? Well, if I'm summing the list, then the so far result is the sum of the items I have processed so far. So I'll write the accumulative helper. And if the list is empty, then there's no more items to add, so I just produce the result so far because that's the final answer. Otherwise, so in my recursive case, I want to compute the sum of the rest of the list, and I update the accumulator, that which I'm taking with me, my result so far, by adding the result of the first item to the result I've seen so far. And now, of course, I need a helper, or sorry, not a helper, a wrapper. Which is just going to be that there. So my initial sum is just 0. Both of these functions work, but how we trace through them is actually quite different. So I'll do on the board here the simple one first. I'm going to do simple over here and accumulative over here so you can see the two side by side. All right. So if I call sum simple on this list here, then, and this is a condensed trace, so we're going to leave out a lot of the steps, but this is going to give me plus 1 The next application gives me this. And then we get which we know some steps later gives me 6. Do you see where the combination happens? Now, if we take the same list as input and we do this with the cumulative recursive function, it's going to look a lot different. Now, actually, I'm just going to use the Accumulative Recursion function because I don't want to use the wrapper. So we're going to do list 1, 2, 3, and my cumulative starts out at 0. So that's the first recursive application. Here's the second. Isn't that interesting? When we return, we get the value from the function. We don't have to do anything. We have the answer. Technically, by the way, this is empty. That's what I should have been writing over there. The result builds up in a different place. In order to get the result of 6 here, we actually have to go deep, 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 and we don't actually end up summing the answer until we reach the base case, and then after the base case is reached, now we've got this giant expression that we have to evaluate, and then we evaluate and get the final result. With accumulative recursion, we take the answer with us. We compute the answer as we go. When we reach the base case, we produce the answer. We don't have to do anything else. So how these two functions actually trace through is quite different. And if you're asking me, if I'm sitting down to do some recursion, which one am I going to choose? I almost always choose accumulative. It's usually, for me, the easier way to do it. Yeah?
Is there any case where recursion is not as efficient as
I'm sure the answer is yes. But I can't, off the top of my head, think of a case where that would be. I'd have to think about it. All right. So, we can, by the way, here's also a condensed trace of the max list accumulator. And again, what I'm pointing out here is instead of the work of computing the max happening outside, it's now all happening in that accumulator. So what we see here is we have the list 1, 2, 3, 9, 5. Our accumulator starts out at 1, then it becomes 2, 3, and then it's 9. Once the list is empty, there's no more work to do. We just produce 9 and we're done. We take the answer so far with us. Now, there's a couple slides here. I'm not going to cover them because we've kind of already talked about this. Before I talk about this particular example here, if you're having a hard time seeing where cumulative recursion can be used or how to use it, here's my recommendation. If you look at the previous few modules where we've talked about recursion, everything has been simple recursion. So take every one of those functions that is in modules like 6, 7, and 8 and convert all of them to a cumulative. It's not actually that many things. It's like summing a list, checking if a number appears at least n times, merging two lists together, testing for equality. See if you can convert all of the functions that we've done so far to an accumulative one. The answer, by the way, is yes, you can, obviously. Otherwise, I wouldn't ask you to do it. But this would be good practice for you, not just so that to make sure that you understand accumulative recursion, but you know, it's like almost reading week and exams are coming and you should probably start studying more than an hour before the midterm. It's probably a good idea. So, all right. Another example of a function that we can do both with simple recursion or with cumulative is reversing a list. So some of you might have found this function where it's like, give me the numbers from 1 to 10, except when we do it, it ends up counting down. Because if with simple recursion, if you give it n, it will go 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 until it reaches the base case of 0. Yeah, but I want the numbers from 1 to 10 in increasing order, not decreasing order. And in order to do that with simple recursion, we had to have a start and a stop. Well, what if I want the numbers from 0 to 10, but I want them in an increasing order? Well, then I would have to reverse the list that I got. And we can reverse a list with simple recursion. All we have to do here is, if the list is empty, produce empty. Otherwise, reversing the list is as simple as appending the reverse of the remainder of the list to the current element. Now you might be thinking, why didn't I put the current element first? It's because we want to go the other way. So we have to put the result from the rest of the list first. And then our self, which is the old front, we put ourselves at the back. So that's simple recursion. The only problem with this solution is, again, we have two recursive functions here. My reverse is a recursive function, and guess what? So is append. We've done append before. It's recursive as well. And so if we actually count the number of recursive calls that are happening here, it's n squared. I don't like n squared. But let's see its accumulative brother, or sister, whichever you prefer. So if we use accumulative recursion, what we are taking with us, our result so far, is the list reversed so far. And so we start out by saying, well, the reverse list so far is empty. And then what we're going to do is, when the list is empty, we produce the accumulator, which is our answer. Otherwise, we are going to call reverse on the rest of the list, and we update our accumulator by consing the first of the list onto the result so far, which effectively is going to put them in reverse order. And if you do this, you'll note there's only one recursive call. And it only gets called once for each element of the list, which means that if we compute the number of recursive calls, it's big O of n. That is significantly better than n squared. Much, much better. And if we trace through it, you can see how the list that is consumed slowly disappears, while our result so far slowly gets the item added to it. It's kind of cool, actually. All right. Now, there's one more kind of recursion we're going to talk about for now, but we don't have time, and that's generative recursion, which is all kinds of crazy. We will do that on Thursday's class, and then we're going to introduce you to something super fun, and it's going to make your life hopefully a lot easier, called structures. So I will leave that here for today. Go have some fun or something.